Welcome back, everybody, to another deep dive. Today we're heading over to Jupiter to check out one of its moons.
Oh, cool.
Yeah. This moon is called Io, and it's got something like 400 volcanoes.
Wow.
I know, it's the most volcanically active place in the solar system.
So are they like constantly erupting?
Pretty much, yeah.
Yeah.
I mean, picture lava flows and plumes shooting up like all the time.
I mean, that's wild. But how does that even work? Where does all that energy come from?
Right. That's what scientists have been trying to figure out for like decades.
Decades.
Yeah, like since the 70s.
Oh, wow.
And the leading theory, for the longest time was that there's this massive magma ocean underneath Io's surface, like a giant sea of molten rock.
Ah, I see. So that would explain the volcanoes.
Exactly. But new data from NASA's Juno mission is like throwing a wrench into that whole idea.
Juno, the spacecraft.
Yeah. Juno's been orbiting Jupiter since 2016, and it's done a few close flybys of Io.
Hold on. How close are we talking here?
Like crazy close. In 2023 and 2024, Juno zipped past Io at a distance of just 930 miles.
930 miles. That's like flying from New York to Chicago.
I know, right? It's insane to think about a spacecraft getting that close to a moon that's basically one giant volcano.
So what did Juno find out? Did it confirm the Magma ocean theory?
Actually, it did the opposite. Juno's measurements showed that Io is mostly solid on the inside.
Wait, so no giant magma ocean sloshing around in there?
No, it seems like Io's interior is more like a billiard ball than a water balloon.
Well, that's a surprise. But if there's no giant magma ocean, how are all those volcanoes erupting?
That's $1 million question, right? And here's where things get really interesting. The data from Juno suggests that each volcano on Io might have its own individual magma chamber.
So instead of one giant lava cauldron under the surface, we've got hundreds of smaller ones, each powering its own volcano.
That's the idea. It's like each volcano has its own personal furnace.
Wow, that's wild. But okay, let's back up for a second. How did we even discover volcanoes on Io in the first place?
Well, that's a great story. It goes back to 1979 with a scientist named Linda Morabito. She was looking at images from the Voyager 1 spacecraft.
Voyager 1. The one that's now like in interstellar space.
The very same. Anyway, Linda was studying these images, and she spotted something weird, a plume shooting up from Io's surface.
And that's how we found out about Io's volcanoes.
Yep. Just by looking at pictures from a spacecraft millions of miles away.
That's incredible. Talk about an aha moment.
Right. It was a huge discovery. But of course, then the big question became what was causing all this volcanic activity.
And that's where the idea of a global magma ocean came from.
Exactly. Scientists knew that Io is caught in this gravitational tug-of-war between Jupiter and some of its other moons.
It's constantly being pulled and stretched.
Yep. It's like, imagine squeezing a stress ball over and over. That's kind of what's happening to Io.
Ah, so all that squeezing generates heat.
Tons of it. That's what melts the rock and creates magma.
I see. So that's why scientists thought there might be a giant magma ocean under the surface.
It made sense at the time, but as we know now, Juno proved that theory wrong.
Right. Juno acted like this super sensitive scale measuring Io's gravitational pull. And that data told us how Io bulges and stretches, revealing what's inside.
And the verdict. Mostly solid, with these isolated pockets of magma under each volcano.
Okay, so we've got these separate magma chambers, each fueling its own volcano.
Yeah.
But how did they even form in the first place?
Well, one idea is that Io's interior is slowly separating over time, with denser materials sinking towards the core and lighter materials rising.
Kind of like how oil and water separate.
Exactly. This process is called differentiation, and it could create those pockets of magma that feed the volcanoes.
Differentiation, huh? Can you break that down a bit more for me?
Sure. Imagine a giant lava lamp. You know how those blobs of wax rise and fall?
Yeah, I love those things.
Well, it's because the wax has a different density than the liquid around it.
Right.
So in a similar way, different materials inside Io are separating based on their density. And this process can create regions where magma forms.
Ah, so it's like a giant slow-motion lava lamp inside Io.
That's a great way to put it. But here's another question. If these magma chambers aren't all connected, wouldn't they eventually cool down and solidify?
Yeah, that makes sense. How are the volcanoes still erupting after billions of years?
Well, it seems like the tidal heating from Jupiter's gravity is constantly replenishing those magma chambers, keeping them hot and active.
So it's like a cosmic balancing act. The cooling of the magma chambers versus the constant heat from Jupiter's pull.
Exactly. It's a delicate dance. And it's not just about Io either. This discovery has implications for other places in the solar system, too.
You mean like other moons with volcanoes?
Well, not just volcanoes, but think about those icy moons that might have hidden oceans beneath their surfaces.
Like Europa.
Exactly.
Europa's the one that everyone's excited about, because it might have like more water than all the oceans on Earth combined.
It's crazy to think about, right? A moon with more water than our entire planet.
And then there's Enceladus too, Saturn's moon. They think it's got a huge ocean under its icy shell.
So both Europa and Enceladus could have these vast oceans hidden away. And we think those oceans might be warmed by tidal heating, just like Io.
That's the connection, right? But here's the thing. If Io doesn't need a global magma ocean to power its volcanoes, maybe Europa and Enceladus don't either.
Hold on. So instead of picturing these moons with like a giant layer of magma just below their oceans, we could be looking at something more like Io, with these pockets of magma providing localized heat.
Exactly. It changes the whole picture.
But what does that mean for the possibility of life in those oceans? I mean, if there's no giant magma ocean, wouldn't that make it harder for life to get started?
Not necessarily. Think about it this way. Imagine you're a tiny little organism living in Europa's ocean. If that ocean is sitting right on top of a global magma ocean, things are going to be pretty rough.
Yeah, I guess that would be like living in a pressure cooker.
Exactly. You'd be dealing with extreme temperature swings, probably a lot of nasty chemicals seeping up from below. Not exactly a cozy environment for life as we know it.
Okay, that makes sense. So a global magma ocean isn't exactly a recipe for a thriving ecosystem. But what about these smaller, isolated magma chambers?
That's where things get interesting. With localized heating, you could have certain regions of the ocean that are warmer, more chemically rich, maybe perfect for certain types of organisms.
While other areas remain cooler, more stable.
Right. It's like having different neighborhoods within the ocean, each with its own unique character. Some might be better suited for life than others.
So this discovery about Eo's volcanoes might actually be good news for the search for alien life.
It definitely adds a new layer of complexity to the whole discussion. We can't just assume that tidal heating automatically leads to a global magma ocean and therefore no chance of life.
Right. We have to look at each moon, each planet individually and consider all the factors at play.
Exactly. It's all about nuance and detail.
Speaking of nuance, you mentioned earlier that each of Eo's volcanoes might have its own personality. What did you mean by that?
Well, if each volcano is tapping into its own little magma chamber, and those chambers are formed through this differentiation process, it stands to reason that the magma composition could vary from one volcano to the next.
So you're saying the lava erupting from one volcano could be chemically different from the lava erupting from another volcano just a few miles away?
That's the idea. One volcano might erupt with runny bright orange lava, while another spews out this thick dark stuff. It all depends on the specific mix of minerals and gases in each magma chamber.
Wow, so Io could be this incredibly diverse volcanic world with each volcano putting on its own unique show. It's like a planet-sized fireworks display.
Exactly. It's not just one big homogeneous blob of magma down there. It's a complex tapestry of different compositions, different temperatures, different personalities, if you will.
I love that analogy, each volcano with its own personality. But wouldn't that make Io a goldmine of information for scientists? If we could study the lava from each volcano, we could learn so much about the interior of the moon.
You're absolutely right. It would be like taking a core sample of Io. But instead of drilling down, we're analyzing the molten rock that's conveniently being erupted for us.
It's like Io is offering us a free peek into its guts.
That's a great way to put it. And the more volcanoes we study, the more pieces of the puzzle we get.
We've been talking a lot about the implications of Io's individual magma chambers for other moons in our solar system, but I'm curious, what about those exoplanets we keep hearing about?
The ones orbiting other stars.
Yeah. Does Io have anything to tell us about those distant worlds?
That's a great question, and one that scientists are definitely thinking about. You see, many of the exoplanets we're finding are these super-Earths planets, much bigger and more massive than our own.
Super-Earths, huh?
Yeah. And some of these super-Earths are thought to experience extreme tidal heating, way more intense than anything we see in our solar system.
So Io, with its crazy volcanism driven by tidal forces, could be like a model for understanding what might be happening on those super-Earths.
That's the thinking. By studying Io, we can develop better models for predicting the internal dynamics and surface activity of these distant planets. It's like using a small-scale experiment to understand a larger phenomenon.
That's pretty amazing. It's like Io is a key that unlocks secrets about worlds light years away.
And who knows? Maybe some of those super-Earths have their own versions of Io, with hundreds of volcanoes, each with its own unique personality, just waiting to be discovered.
So we've learned that Io is like this crazy volcanic world with hundreds of volcanoes, each with its own little magma chamber. But like you said before, more answers just lead to more questions, right?
Oh, yeah, definitely. Like, for starters, we still don't know exactly how those individual magma chambers formed.
Yeah.
Was it purely through that differentiation process where the heavier stuff sinks and the lighter stuff rises?
Right, the giant lava lamp idea.
Exactly. Or are there other mechanisms at play? Maybe something to do with those intense tidal forces from Jupiter.
Yeah, I mean, it's got to be playing some role, right? It's like constantly squeezing and stretching Io.
For sure. And that squeezing could be concentrating the magma in certain areas, leading to the formation of those distinct chambers.
Ah, so it's like if you squeeze a tube of toothpaste, the toothpaste gets pushed to one end.
Exactly. The tidal forces could be acting like that squeezing force pushing the magma around.
That makes sense. But then there's the question of connectivity. Like,
Well,
are those chambers completely isolated from each other? Or could there be channels or pathways connecting them?
That's another big unknown. It's possible that some of those chambers are linked, allowing magma to flow between them.
Oh, wow. So like a whole network of underground lava tubes.
You got it. And that could explain why some volcanoes erupt more frequently than others, or why we sometimes see simultaneous eruptions from multiple volcanoes.
I see. So it's like Io has a hidden circulatory system, but instead of blood, it's magma.
That's a great way to think about it. And speaking of eruptions, we can't forget about those incredible plumes shooting up from Io's surface. Some of those plumes reach hundreds of kilometers high.
It's mind-boggling, right? Hundreds of kilometers? That's taller than Mount Everest.
And those plumes can tell us a lot about what's going on below the surface, the composition of the magma, the gases being released, even the depth of the magma chamber.
So it's like analyzing the exhaust from a car to learn about the engine.
Exactly. We can get a glimpse into the heart of Io's volcanoes without even having to land there.
That's pretty cool. But of course, a lander mission would be amazing, right? Imagine actually being able to collect samples of fresh lava from Io.
Oh, that would be incredible. We could learn so much about the composition of Io's interior, the evolution of its volcanoes, maybe even find clues about the early history of the solar system.
A mission like that would be groundbreaking, but I'm guessing it wouldn't be easy.
Not at all. You're talking about landing on a moon that's constantly erupting, with volcanoes spewing lava and plumes everywhere. Plus, the radiation from Jupiter is intense.
Yeah, it sounds pretty dangerous. But hey, if we can land a rover on Mars, surely we can figure out how to land on Io.
I have no doubt that engineers will come up with something brilliant. But in the meantime, there's still so much we can do from Earth. We can use telescopes to monitor Io's volcanic activity, track the movement of lava flows, analyze the composition of those plumes.
And with computer models, we can simulate Io's interior and test different hypotheses about how those magma chambers work.
Right. It's all about combining observations and modeling to build a more complete picture of this fascinating world.
So even though we've overturned this long-held idea about a global magma ocean, we've opened up a whole new set of questions and mysteries.
That's the beauty of science, right? Every answer leads to more questions. It's a never-ending quest for knowledge.
Well, on that note, I think we've reached the end of our deep dive into the fiery world of Io. What an incredible journey it's been.
I agree. It's amazing how much we've learned about this little moon and how much it can teach us about other worlds, both in our solar system and beyond.
Exactly. And to our listeners out there, I hope this deep dive has sparked your curiosity. If there's one thing we want you to take away from this episode, it's this. Keep asking questions, keep exploring, and never stop learning about the amazing universe we live in. Because who knows what other incredible discoveries are waiting out there just waiting to be uncovered.